Now that we've finished the first take-home quiz, we're going to go back and revisit some of the things that we skipped earlier in the semester, some of the sections that we passed over. Um, and how appropriate that I'm also filming this on the Passover. Maybe that's not actually connected. So we're going to go over. We're going to pick up some of the sections that we skipped. In particular, today we're going to focus on sections 6.2 and 6.3, where we're going to introduce a new idea called binomial distributions. An important note, when you look next in your notes, is section 11.1. I love 11.1. It's a great section, but due to time constraints and coronavirus, we're going to skip section 11.1. So if you want to just learn more statistics, go read that section. It's really interesting and it's a really good section. But for us, we're going to focus on 6.2 and 6.3. And the big idea of 6.2 and 6.3 is this idea of a binomial distribution. And you can see in this word binomial that we have the prefix bi, and so you might be able to predict what's going on in a binomial distribution. Maybe not, but the bi means two. And so a binomial situation is an experiment that has only two possible outcomes. So binomial experiment has only two possible outcomes. So what are some examples of binomial experiments? Well, if you flip a coin, you can have heads or tails. There are only two outcomes when you flip a coin. You can get heads or tails. Today, as I film this, Bernie Sanders dropped out of the Democratic primary, which means our presidential election will most likely be Trump and Biden. And so everyone will have a choice. Now, there actually are other people on the ticket. I sometimes vote for those people because I don't like the main people. But let's just pretend that for all practical purposes, the election has only two choices. You can either choose Trump or you can choose Biden. There's only two possible outcomes. One of the reasons why binomial experiments are super important, though, is anytime you do science, there are always only two results that can show up in your science experiment. And that is, you can have a success or you can have a failure. And this ends up being a really popular thing in science. So you run a bunch of experiments. How many of those worked? How many didn't work? And that splits you in there. But binomial experiments always have two outcomes, only two outcomes, not more than two outcomes. Okay, so because of this, we want to kind of think about how to analyze and do math with situations that have only two possible outcomes. So the math of heads and tails. Now in section 6.2, what we're going to do is we're going to learn how to calculate these. And what I would love to do is go through class and have you calculate a bunch of these on your own. But let's just do a couple of those for ourselves. So for example, if n equals 2, then let's just think of that. What does that mean? That means you flipped two coins. And so you really had two options. You can have heads, 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 tails, tails, heads, or tails, tails. And so that means, what the binomial probability does is a binomial experiment counts the number of heads. So the binomial counts the number of, well, it could be heads or it could be tails. It's whatever you're dealing with. And so, and a binomial probability has a probability attached to each outcome showing up. So notice when you flip a coin, that is a 50-50 binomial experiment. There's a 50% chance of heads, 50% chance of tails. When we get to the election, it's not going to be 50-50, and that is one of these candidates will have some sort of lead. It'll probably be pretty close, though. It'll probably be, 55-45 or something, just knowing the way party politics works in America. If you're running an experiment, there could be a really big difference between success and failure. So, for example, if you're building things in a factory, hopefully you have like a 90-something% chance of success and a very small chance of failure when your items are built in a factory. So you can have very big differences between success and failure for your probability. So a binomial experiment has a probability attached to it. Now, in this case, when we're flipping a coin, if it's 0.5, then what you'll notice is that we have 3 outcomes. You can have 0 heads, 1 head, or 2 heads. And the probability of getting 0 heads is going to be 25%. The probability of getting 1 head, notice there are 2 ways to do that, so that's 50%. Probably getting 2 heads is also 25%. So this is what comes out if we have a 0.5 probability. Okay, let's tackle what would happen if we flipped more coins. If we flipped more coins, say we had n equal to 3, n equal to 3, and again, we're going to have that same 50% probability, so assume that everything is the same chance. Well, now we could have heads, 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 tails, heads, tails, heads, tails, heads, heads, head, tail, 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 head, tail, 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 head, or tail, tail, tail. Turns out there are 8 different ways this could show up. And now we can put our probabilities like this. And we can have 0 heads, 1 heads, 2 heads, or 3 heads. 0 is only 1 out of 8, or 0.125. 1 head, we had 1, 2, 3 out of 8, or 0.3. Oh, what is 3 out of 8? Hold on. 375? Is that the 375? Good. Okay, 0.375. 2 heads. Oh, this is the 0. Sorry, the 0 is all tails. 1 head is 1, 2, 3. 2 heads is also 1, 2, 3. 1, 2, 3. Uh-oh. Man, I messed up writing those things down. Sorry about that. 2 heads, we've got 1, 2, 3 way of doing those. That's 0.375. And 3 heads, there's only one way to do that. So that's 0.125. And what you can see is as we flip more and more coins, these numbers get more and more dispersed. And so what we're really interested in is all of the possible results. Well, in an ideal world, I would take the time and we would figure out how to calculate these and calculate these for all probabilities, and we would come up with a really lovely formula, and that formula looks like this. The probability that x equals k, so that means if we've got this table and we have the k column in the table, what number shows up in there? The number ends up being n factorial over k factorial, n minus k factorial, p to the n, p to the k, and 1 minus p to the n minus k. Isn't that a lovely formula? What are factorials, by the way, in case you don't remember? A factorial, like 5 factorial, is 5 times 4 times 3 times 2 times 1. So you multiply every number less than that. Okay, so this is a formula that works. Do you want to know the good news? We are not going to use this formula. Instead, we will not use this formula. We will use the calculator. So we're going to use our calculator to do it because this formula is built into your calculator. So let's get your notes out. Go to page 58, and this is where we're going to kind of learn how to calculate some of these things on our calculator. So what we're going to do is to make your calculator run this, you need to find the DISTR button, and this is the button we've used before. This is where normal CDF, inverse normal, TCDF, inverse T, this is where all of those things are located. And we're going to look for the binomial PDF button. And so if I come over here, and so we'll go to binomial PDF, and then that PDF is going to have 3 things that need to be entered. We need to enter N, we need to enter P, and we need to enter K. N is the total number of experiments. P is the probability of success for each experiment. And K is the number of successes. So if I wanted to do, say for example, this problem that we did earlier where we had 2 dice, or we had 2 coins, then what I would do is I would say we did 2 times, so we flipped our coin 2 times, so I'm going to put 2 in for my n. If I wanted to find the probability of getting 1, the probability is 0.5 because a coin has a 50-50% chance of being heads. And then finally, if I wanted to figure out this number right here, what's the probability to get 1 head, I would let k equal 1. So if I type binomial PDF with 2, 0.5, and 1, and I think some of you have a menu where you can just put these numbers in your menu. If you don't have a menu, you just type them in order. Now, my calculator doesn't have a menu because it's quite a bit older. Well, let's go distribution. Let's come down to normal binomial PDF. So there it is. By the way, this is the only time we use a P because we're looking for a specific value. So binomial PDF, I'm going to put 2, comma, 0.5, comma, 1. And if this works, it should give me this 50% number. It should tell me this answer that shows up right here. So let's hit enter and see if that works. So I'll hit enter. And I got 0.5, which is that number. Okay. Now, let me teach you one more command. And this is if I switch PDF to CDF, then what CDF will do is CDF will add all values less than or equal to whatever your k is. So now, instead of k being the number of successes, you add up all of the terms. So if I do that same command with CDF, instead of getting 0.5, I get 0.5 plus 0.25. So I should get 0.75 when I do my calculation. So let's try that out with binomial CDF and see how that works. So we'll go distribution. We'll scroll all the way down to binomial CDF, which is right here. I'll hit enter. And then I'll do the same numbers, 2, 0.5, and 1. And so this is going to give me the answer for 1 and the answer for 0. It's going to pick all numbers less than 1. And so I hit enter, and I get 0.75. So it added these 2 answers together to give me my result. Okay, so this is how the binomial command works. Why don't you read this problem that we've got, exercise 6.3. This would be a great time for you to try it out on your own. See if you can make that command work in your calculator. So take a pause, see if you can make it work. Okay. So what we're talking about here is Lionel Messi, who scores a goal about 23% of his shots. By the way, those of you who are interested in soccer, that's outstanding. Well, it's not surprising. Everything he does is outstanding. It turns out that Messi scores a lot of shots. He also takes a lot of shots. So that's why he is who he is. Okay, so we want to say if Lionel Messi takes 6 shots in a game, what's the probability that he does not score a goal? So I just need to know what are those 3 numbers that I put into my calculator. N is how many experiments we had. Well, each shot was an experiment, so N was 6. P was the probability of success. In this case, success was scoring a goal, so 0.23 is the probability of success. Finally, K is how many successes we have. So we want to know what's the probability of not scoring a goal. And so 0 is the number that comes out. So I'm going to go to binomial PDF. The way you can remember, right, is P is just finding a single probability, just one. CDF is cumulative, so it's adding up all those probabilities together. So I'm going to type that in my calculator, and I'm going to put 6, comma, 0.23, comma, 0. Again, you may have a menu to hit enter. And when that works out, I got 0.208 for this answer. So about a 20% chance of not scoring a goal. Okay. Let's move on to part B. And part B says, what's probably he scores 3 goals. So what's going to happen on part B? We're going to have the same number of experiments because he had the same number of shots. P is 0.23 because he's the same probability of having a success. K, however, is the number of successes. Now we're interested in calculating the probability he scored 3 goals. So I'm going to put 3 on here. Okay. Now we're going to do the same thing with binomial PDF. We're going to enter those numbers in our calculator. And so I'll have 6.23, and now I'll just change that last number to 3 and hit enter. And I got 0.111, so about 11% chance of a hat trick, which is pretty outstanding. Okay. Finally, what do we do for part C? Not finally. So for part C, we're going to find the probability of having 2 or more goals. There are a few ways of tackling this. Let's tackle it in, there's a few ways of tackling this. I'm going to tackle it going from the most complicated to the simplest. So one, what's the probability of finding 2 or more goals? Well, you could have the probability of 2 or more. We could do 2 goals and then find the probability of 3 goals, 4 goals, 5 goals, and 6 goals. And so we could do like these problems on A and B. And so we could do 1, 2, 3, 4, 5, and we could add all of those together, and that would be the correct answer. Another option, if you're kind of playing along at home, another option would be to find the probability of 0 goals and the probability of 1 goal. And so we could put those together, and this is not our answer, but this is 1 minus our answer. So I saw earlier that 0 goals was 0.208. 1 goal is going to be 0.373. And so those numbers come out to be that 0.581. And so our answer is 1 minus that number. And so our answer is 0.418. Because this is the probability you score 0 or 1, so 2 or more is 1 minus that, because we have to make it all add up to 100%. Finally, there's one last option we could have done. And the last option was we could have used the binomial CDF command. And if we wanted to use the binomial CDF command, what would I have done? I would have done n equal to 6, p equal to 0.23, and k equal to 1. And that right there should give us this 0.581 answer, because that'll give us 1 and everything lower than 1, and then we would have to subtract 1 from our answer. So we could have got this 0.581 by adding the 2, or we could have got the 0.581 by using the binomial CDF command, just like that. 0.23, 1, and hit enter, and we get, I messed that up. I was just checking on my calculator, and it comes out to be the same. Maybe I should have rounded that to 582. Okay, that's fine, no big deal. I'll go ahead and round it because I can't deal with things like that. Okay, finally, let's look at part D and see what happens on part D. So part D, we've changed it up a little bit. And so part D, we've said Messi is now going to take 254 shots. And we want to know what's the probability that he scores exactly 75 goals. So that means we now have 254 shots. And our P is now 0.23, and our K is 75. So we come back to binomial PDF, and we put these numbers in. So you can see it here if you want. Good luck reading my screen. 254, 0.23, 75. And we'll hit enter. And this number is very, very small. This number is 0.003. So this means there's only a 0.3%. Why is it so small? This doesn't seem like a ridiculous result, right? If we do 75 divided by 254, that's 29%, which isn't that much higher than the 23%. The reason why this is so small is because any individual goal number is going to be very unlikely, right? So there are 254 shots. To guess exactly how many shots you get, every single guess is going to be really small because there's so many possible guesses. If we switched it to binomial CDF, however, and we did binomial CDF, and we did 254 and 75, and 0.23 and 75, we would get a number that's much larger. In fact, we get a 99% chance. So that's not telling us 75 goals, that's saying 75 or less. So most likely, he's going to score less than 75 goals. Okay, hopefully through this, you're just learning how to type those things in your calculator. If you're having trouble with your calculator, don't hesitate coming to see me. This is the type of thing that you need to be visiting my study hall hours and getting these things straightened out. Okay, let's look at exercise 6.4. And I want you to try this on your own. So pause your calculator, read exercise 6.4, and see how it goes. Okay, so what we're doing is we're rolling 5 dice. We want to find the probability 2 land on a 6. So we could think of this as a binomial because we can think of it as either it lands on a 6 or it doesn't land on a 6. We have 5 dice. That's how many experiments we ran. The probability of landing on a 6 is 1/6. And we want to know the probability of getting exactly 2. So I'm going to use that binom PDF button. I'm going to put this for my N, P, and my K. And we're going to see what we get. Okay, give me just a second to type it in. So for my N, I'll do 5. For my P, I'll do 1/6. And for my K, I'll do 2. And I'll hit enter. And I got 0.1607, 0.161 sounds good. So I got 0.161 for my probability. Hopefully you're able to do this. Hopefully you're able to make your calculator work these computations correctly. All right. Let's jump on ahead to the next problem and kind of see what's going on. Let's go ahead and jump ahead to section 6.3. Let's go ahead and jump ahead to section 6.3. And to do this, we really just need 2 formulas. The first formula is what is the mean and what is the standard deviation for a binomial experiment. And it turns out that these numbers are pretty straightforward. The mean is the one that makes a lot of intuitive sense. So if I said Messi makes 23% of his shots and he shot 254 shots, how many do you think he made? What you would do is you would just take 23% of the 254. You would just combine that probability with the number. And that is exactly how we do the mean. The mean is just how many experiments you have times your probability. And so this formula for the mean makes a lot of sense. The standard deviation is less intuitive, so I'm going to just write it down. It is n times p times 1 minus p, and then we have to take the square root of these things. So this is our standard deviation formula. It is less intuitive. Let me just say a few words about why this might make sense. First, if you think if you had a probability of 0, then you would have no standard deviation because you would always get no, right? You'd get failure every single time. And so notice you get a 0 standard deviation if the probability is 0. Similarly, if your probability is 100% or 1, you would get true every time. So you'd have no standard deviation. There'd be no change in your values. And so we get 0 as well with that. So notice this gives us 0 on the 2 extremes when the probability is 1, when the probability is 0. And then as the numbers are in the middle, it kind of figures out the right answer. So this isn't exactly right. We could spend the time. You all are capable enough. We could spend the time to derive this formula, but this is just not one that really fits with the type of things we're trying to do this semester. Okay, so what I want to do is I want to come calculate the mean and standard deviation, and this is one of the easiest types of problems that we'll do all semester. So let's just come to exercise 6.5. I'll let you all do part A on your own if you'd like. What would I do for part A? I would take that binomial PDF button and do it with k equals 0, 1, 2, 3, 4, 5, 6, and write all those probabilities down. And I think you all are capable of doing that. It's a little tedious, but we could do this. And write those probabilities down and then graph them. Okay. But for part B, what's the expected number of goals? The expected number of goals is the mean, which is, well, our n here was 6 because we were doing 6 shots in a game. And we've got 23%, so we'll multiply 6 by 0.23. And we'll put those together. And we'll get 1.38. So when Messi takes 6 shots in a game, you'd expect him to score somewhere between 1 and 2 goals, 1.4 goals. Okay. How about the standard deviation? What's the standard deviation of the number of goals you'd expect? Well, we just take the square root. We take that 6. We take the 0.23, and then we take 1 minus 0.23, which is 0.77. Notice these two numbers always have to add up to 100%. So whatever that number is, you take the complement of it, the number that makes it add up to 100%. And now this, we just simply type into our calculator and come up with our answer. And we've got 1.03. So when Messi shoots 6 shots, he averages 1.38, and he has a standard deviation of 1.03. So it gives you some picture of what it looks like when he shoots. Okay. Let's flip over our notes one more time. I'm trying to cover a lot of ground in this video because I don't want us to invest just a ridiculous amount of time on these problems. But at the same time, I want us to actually understand what's going on because it'll set up our sections 8 and 9, which is really where I want to get to, 8, 9, and 10. But let's talk about exercise 7.6. The real idea of 7.6 is this, and that is that what if we were to take some of these binomial experiments, and what if we have a binomial experiment where, say, n is 2? Well, that graph only has 2 options. Either you have 0 successes or 1, and they both have their probabilities, whatever they are. They have to add up to 100%. Okay. What if n equals 3? Then you have your options. You could have no successes, 1 or 2 successes. These two end up being a little bit smaller, and the one in the middle ends up being a little bit bigger because your most likely result is that one ends up being true and one ends up being false. Well, that's not necessarily the case. You could end up with a binomial experiment that has a really big or really small probability. For example, if you're buying lottery tickets, most of your probability is going to be 0, that you did not win the lottery. And so you have 1 and then really tiny things over there. Okay. But here's the real question is what happens as n gets really big? So as n, let's do one more. Let's do n equals 4. We would end up with, we only have the possibilities of 1, 2, 3, 1, 0, 1, 2, or 3. Oh, wait. This is a 1. I don't know why I'm getting all my numbers wrong here. If we have 3, then you'll kind of have low probabilities on either of these ends, and then the probabilities in the middle will be larger. And this might be a reasonable type of graph. But the question is, what happens when n becomes really large? So let's do n is really big. If n is really big, then you end up with a situation that looks like this, where your values on the side are very small, but then in the middle, they kind of grow, and then they duck back down again. Well, what we know from the central limit theorem is that no matter what happens, this probability will always start to look like a normal distribution. And so if n becomes really big, these probabilities start to take that same normal distribution shape. But moreover than that, we know exactly what the mean and the standard deviation for this normal distribution should be. We know the mean is n times p, and we know the standard deviation is the square root of n times p times 1 minus p. Now, one thing we're going to do is when we move to chapters 8 and 9, we're going to try to, when we go to chapters 8 and 9, we are going to do confidence intervals and then hypothesis tests with binomial data. And that's really what we want to do. We're going to revisit those ideas of confidence intervals and hypothesis tests, except we want to do it in this new setting where we have binomial data instead of the data like we've had in the past. Okay, well, how is this going to work? Well, what this is going to work is we're going to have that same formula we had, except instead of having an average, you can guess we're going to have something that looks like this. We're actually going to divide by n to make everything between 0 and 1. And then if we divide by n here, this becomes divided by a square root of n. So what we'll see is we'll have the places where the average went in, the place where x bar goes, and the place where mu goes, we'll have just p's. And the place where the standard deviation went, instead of having the standard deviation, we're going to have a p times a 1 minus p, square root of p minus 1 minus p over the square root of n in its place. So as we move to the next formulas, our formulas will stay basically the same with the means and the standard deviations in them, but the big difference is we'll now have p's in our formula, and we'll be using this known mean and known standard deviation to plug into our old formulas. All this is to say that 7.6 is a very interesting section. I would like you to learn it, but you may skip your 7.6 homework. So don't feel like you have to turn in your 7.6 homework. Okay, so as a takeaway from today, we're going to skip chapter 11. We're going to skip the 7.6 homework, but I do want you to do the 6.2 and the 6.3 homework, just so we can get a feel for what are binomial probabilities and how are these probabilities calculated. All right, so good luck with that, and when we come back next time, we'll learn how to do confidence intervals and hypothesis tests with binomial data instead of the more traditional data.